Introduction to String Theory. Good evening, dear listener. As you settle into your comfortable space, allow your mind to drift gently into a state of relaxation. Imagine yourself floating effortlessly through a vast, serene cosmos where stars shimmer softly against the velvet expanse of space. In this tranquil journey, we will explore the concept of string theory, a framework in theoretical physics that seeks to unify the fundamental forces of nature by proposing that the basic constituents of the universe are not point-like particles, but tiny vibrating strings. The quest for unification. For centuries, physicists have sought to understand the fundamental forces that govern the universe. 4 such forces have been identified. Gravity, the force that attracts 2 bodies toward each other, governing the motion of planets, stars, and galaxies. Electromagnetism, the force responsible for electricity, magnetism, and light, governing the behavior of charged particles. Strong nuclear force, the force that binds protons and neutrons together in the nucleus of an atom. Weak nuclear force, the force responsible for radioactive decay and certain nuclear reactions. While the electromagnetic strong and weak forces have been successfully integrated into the standard model of particle physics, a framework that describes the behavior of subatomic particles, gravity has remained elusive in this unification. The challenge lies in reconciling Einstein's general theory of relativity, which describes gravity at macroscopic scales, with quantum mechanics, which governs the microscopic realm. The emergence of string theory. In the pursuit of a unified theory, physicists proposed string theory. At its core, string theory suggests that the fundamental building blocks of the universe are not zero-dimensional point particles, but one-dimensional strings that vibrate at different frequencies. These vibrations correspond to the various particles observed in nature. For instance, a string vibrating in one manner might manifest as an electron, while a different vibration could appear as a photon, the particle associated with light. This elegant framework offers a potential solution to the unification problem by providing a common foundation for all particles and forces. The diverse particles we observe are simply different vibrational states of these fundamental strings. Extra dimensions and the fabric of reality. One of the intriguing aspects of string theory is its requirement for additional spatial dimensions beyond the familiar 3 dimensions of space and 1 of time. Specifically, the theory posits the existence of up to 10 or 11 dimensions. These extra dimensions are thought to be compactified or curled up at scales beyond our current observational capabilities. Visualize a 2-dimensional sheet of paper rolled into a tight cylinder. From a distance it appears one-dimensional, but upon closer inspection, the second dimension becomes evident. The shape and size of these compactified dimensions play a crucial role in determining the properties of our observable universe. Different configurations can lead to variations in the physical constants and particle behaviors we experience. The beauty and challenges of string theory. String theory is lauded for its mathematical elegance and its potential to unify all fundamental forces. However, it also presents significant challenges: lack of experimental evidence. The energy scales at which string effects become noticeable are currently beyond our experimental reach, making direct verification challenging. Multiple solutions. The theory allows for a vast number of possible solutions, leading to the concept of the string landscape, which complicates the prediction of specific physical properties. Despite these challenges, string theory has provided deep insights into the nature of black holes, the early universe, and has fostered advancements in mathematics through concepts like mirror symmetry. As we conclude this introductory segment, let your mind ponder the profound idea that the universe's diversity stems from the symphony of tiny vibrating strings. In our next segment, we will delve deeper into the mathematical foundations of string theory and explore its implications for our understanding of space and time. The mathematical foundations of string theory, the Polyakov action and worldsheet. At the heart of string theory lies the concept of the worldsheet, a two-dimensional surface that represents the history of a string's motion through space-time. Imagine a string moving over time. The trail it traces forms this worldsheet. The dynamics of the string are described by the Polyakov action, a mathematical expression that encapsulates the string's behavior. This action is integral to understanding how strings propagate and interact within the framework of the theory. Conformal field theory. On the worldsheet, the physics on the worldsheet is governed by a type of quantum field theory known as conformal field theory, CFT. CFTs are characterized by their invariance under conformal transformations, which preserve angles but not necessarily distances. This symmetry plays a crucial role in simplifying the complex equations that describe string interactions, allowing physicists to make precise predictions about the behavior of strings. Virasoro algebra and constraints within the context of the worldsheet. The symmetries of the theory are encoded in a mathematical structure called the Virasoro algebra. This algebra imposes specific constraints, known as the Virasoro constraints, which ensure the consistency of the theory. These constraints are vital for eliminating unphysical states, such as those with negative probabilities, from the spectrum of possible string vibrations. Critical dimensions and anomalies. One of the intriguing outcomes of the mathematical formulation of string theory is the determination of the critical dimension, the specific number of space-time dimensions required for the theory to be free of anomalies, inconsistencies that could render the theory invalid. For bosonic string theory, this critical dimension is 26, while for superstring theory, which incorporates both bosons and fermions, it is 10. These additional dimensions are hypothesized to be compactified or curled up at scales beyond our current observational capabilities, a concept we touched upon in our previous segment. Moduli space and string interactions. The possible shapes and sizes of these compactified dimensions are described by a mathematical space known as the moduli space. Each point in this space corresponds to a distinct configuration of the extra dimensions, leading to different physical properties in the observable universe. Understanding the structure of the moduli space is essential for predicting how strings interact and how these interactions give rise to the particles and forces we observe. T-duality and mirror symmetry. String theory exhibits fascinating symmetries that have profound implications for its mathematical structure. T-duality is a property that suggests strings propagating on a circular dimension of radius r are physically equivalent to strings on a circle of radius 1 lar. This duality implies that large and small scales are interconnected in a non-intuitive way. Similarly, mirror symmetry is a phenomenon where two different Calabi-Yau manifolds, geometric structures used to compactify extra dimensions, can lead to identical physical theories, highlighting the rich mathematical tapestry of string theory. As we conclude this segment, let your mind wander through the intricate mathematical landscapes that form the foundation of string theory. In our next segment, we will explore the profound implications of string theory on our understanding of space and time. String theory's gentle tapestry of space and time. In this segment, we'll explore how string theory offers a serene and fascinating perspective on the nature of space and time, inviting us to ponder the delicate threads that weave the fabric of our reality. The essence of strings in our everyday experience. We think of the world as being made up of tiny particles, like grains of sand that combine to form everything we see. String theory suggests a different picture. Instead of point-like particles, the fundamental building blocks of the universe are tiny vibrating strings of energy. Imagine each string as a minuscule vibrating filament, much like the strings of a musical instrument. The way these strings vibrate determines the nature of the particles they form, just as different vibrations of a violin string produce different musical notes. A symphony of dimensions. Our familiar world has 3 dimensions of space, length, width and height, and 1 dimension of time. However, string theory proposes that there are additional dimensions beyond these 4. These extra dimensions are thought to be compactified or curled up in such a way that they are imperceptible to us, much like how a tightly rolled up piece of paper might appear one-dimensional from a distance. The specific way these dimensions are compactified influences the vibrations of the strings and consequently the properties of the particles they form. The dance of space and time in the serene framework of string theory. Space and time are not rigid and unchanging, but are dynamic and interconnected. The vibrations of strings can stretch and warp the fabric of space and time, creating gentle ripples that propagate through the cosmos. This perspective invites us to envision the universe as a vast flowing tapestry, with threads of energy weaving together the patterns of existence. A harmonious vision. String theory offers a harmonious vision of the universe, where all forces and particles arise from the same fundamental strings. This elegant framework suggests that the diverse phenomena we observe, from the light of distant stars to the gentle pull of gravity, are manifestations of the same underlying essence. It's a reminder of the unity and interconnectedness of all things, inviting us to appreciate the subtle beauty of the cosmos. As we conclude this segment, let your mind drift through the tranquil expanse of this harmonious universe, where the gentle vibrations of tiny strings weave the fabric of space and time. In our next segment, we will explore the concept of supersymmetry and its role in this elegant tapestry. The gentle balance of supersymmetry. In this segment, we'll explore the concept of supersymmetry, a graceful theory that suggests a harmonious balance between the fundamental particles of nature, inviting us to ponder the delicate equilibrium that underlies the fabric of our reality. To adore the dance of particles. In the realm of particle physics, all particles are categorized into 2 families. These particles, such as electrons and quarks, are the building blocks of matter. They follow the Pauli exclusion principle, meaning no 2 fermions can occupy the same quantum state simultaneously. The bosons. These particles, like photons and gluons, are force carriers. They mediate the fundamental forces of nature and can occupy the same quantum state, allowing them to act collectively. Supersymmetry, often abbreviated as SUSY, proposes a serene symmetry between these 2 families. It suggests that for every fermion there exists a corresponding boson, and for every boson, a corresponding fermion. These partner particles are known as superpartners. This elegant symmetry implies that the universe maintains a delicate balance at the most fundamental level. Adore the quest for superpartners. Despite the beauty of supersymmetry, these superpartner particles have yet to be observed experimentally. Physicists continue to search for evidence of supersymmetry in high-energy experiments, such as those conducted at the Large Hadron Collider. The discovery of superpartners would provide profound insights into the nature of the universe and support the elegant framework of supersymmetry. Adore the quarter segment. Let your mind drift through the tranquil expanse of this harmonious universe, where the gentle balance of supersymmetry weaves the fabric of reality. In our next segment, we will explore the concept of extra dimensions and how they might shape the cosmos we experience.
The hidden dimensions of the universe. Imagine, dear listener, that as you drift deeper into relaxation, the universe reveals subtle layers beyond our familiar perceptions. In this segment, we'll explore the intriguing idea of extra dimensions, hidden realms that, according to string theory, weave the intricate fabric of our cosmos. Beyond the visible dimensions in our everyday experience, we navigate a world defined by three spatial length, width, and height, and one dimension of time. However, string theory suggests that there may be additional dimensions beyond these four. These extra dimensions are thought to be compactified or curled up in such a way that they are imperceptible to us, much like how a tightly rolled up piece of paper might appear one-dimensional from a distance. The garden hose analogy. To visualize this concept, consider a garden hose lying on the ground. From a distance, the hose appears as a simple line, one dimension, yet, upon closer inspection, we see that it has a circular cross-section, revealing a second dimension. Similarly, the extra dimensions proposed by string theory are compactified at scales beyond our current observational capabilities, remaining hidden from our everyday experiences. Calabi-Yau manifolds, the shapes of hidden dimensions. The specific way these extra dimensions are compactified influences the vibrations of strings and consequently, the properties of the particles they form. In string theory, these compactified dimensions are often envisioned as complex geometric structures, known as Calabi-Yau. These intricate shapes provide the framework within which strings vibrate, determining the fundamental characteristics of our universe. Implications for the nature of reality. The existence of extra dimensions offers profound insights into the nature of reality. Unification of forces. These hidden dimensions may provide the key to unifying the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces into a single coherent framework. Parallel universes. Some theories suggest that these extra dimensions could harbor parallel universes, each with its own distinct laws of physics and unique properties. New particles and phenomena. The presence of extra dimensions could give rise to new particles and forces potentially observable through high-energy experiments and cosmic observations. As we conclude this segment, allow your mind to wander through the hidden dimensions that may permeate our universe, contemplating the unseen realms that shape the reality we experience. In our next segment, we will explore the concept of M-theory, an extension of string theory that seeks to unify the various string models into a single, all-encompassing framework.